Anyway, couldn't find a slide of the original Cray-1, but Cray-1S is pretty close. The reason to show it here is look and think for a moment about the numbers, because when I come to the last slide, I'm going to put them all together in a chart for you. But here is a single processor machine. Clock period is 12.5 nanoseconds. 80 MIPS is the hardware speed, and 160 megaflops. Here's the packaging. This module I think many of you have seen. You know, it takes two hands to hold it. It's pretty heavy. It's really two-dimensional in the sense that there is a very minimum of interconnection between the two boards and the two sides of the module. And I want to contrast that with the later modules, which are truly three-dimensional. The circuits here are packaged in a very conventional way, hermetically sealed, have leads you bend and poke through the board. 4 gates, silicon. Here we see the Cray-2. Now, this is the one I struggled with because I couldn't get fast enough parts to do what I wanted. Had to make do. Memory is really PC computer memory. As many of you know that have run programs that are memory limited. That's too bad, but you have to use what you could get. Likewise, the silicon circuitry. Not really much faster than Cray-1, but larger scale integration. So there was some progress, and in a vector sense, we achieved essentially the goal I wanted, which was 4 nanoseconds. Came close enough, and managed to get 4 processors in the machine at essentially the same cost as the Cray-1. We allow for inflation in the period in between, keeping a fairly constant cost from machine to machine. Number of MIPS is up substantially because of the 4 processors and because of the clock rate. Likewise, megaflops. The really exciting thing here was to use liquid immersion cooling. When I first talked about liquid immersion cooling, everybody in the project laughed. In fact, they rolled in the aisles. Because everybody knew the boards would swell up, and it just wouldn't work. Nevertheless, we needed something pretty dramatic because we weren't getting very far with cooling with metal conduction. With the densities one has to have, the speed goes up. So we tried it, and what do you know? The boards didn't swell up. Actually, it worked pretty good. And today, I believe that Cray-2 reliability is as good or better than most anything else you can find. And a lot of the reason for that is the liquid immersion cooling. There's very little temperature difference between the parts during warm-up and during normal operation. And so we have good temperature stability, and that's a real key to reliability in the long run. Now, notice the person standing here, because that person is going to appear next in the Cray-3 slides. Not the immediate one, but the following one. Same person, all right? This is the Cray-2 module. Now, I thought this was truly three-dimensional. It isn't a cube, not physically, but it's a cube electrically. Because if one counts the number of lines that are going in the X direction and the Y direction on the boards, the foil runs inside the printed circuit boards. You count those numbers, and then you count the jumpers that are going perpendicular to the board. You find that the populations in all 3 directions are nearly equal. And the preferred one, of course, is the one that goes vertically because it's so short. And so the machine was organized for the really critical transmission paths to be vertically through the module. There are 8 boards here. And so if you looked at it electrically and you counted the integrated circuit packages, it's 8 by 12 by 8, which is very close to a cube. So I was pleased with this, and with the liquid cooling, it seemed to work just great. And although the circuits were slow, we did the packaging job. That's how I felt about it. You notice that the logic levels per clock period is only 4, and tradition is 8. And that's where you find the scalar performance slipping with respect to vector. No point in slowing the vector down. Might as well do whatever you can. But this caused an imbalance between the scalar and vector performance, and it was strictly a function of the slow circuits. Here we see the same person in the Cray-3 computer. Now, here the clock period has dropped to 2 nanoseconds, but the level of logic is 8 again. So here is the dramatic increase in serial speed. It is essentially 3 times what we can do in silicon today with equal effort, equal teams. We're comparing 2 nanoseconds with 6 nanoseconds with the same amount of logic being done per clock period. We have 16 processors, so there's the other big factor of 4. And now the numbers are getting more zeros after them. We have 8,000 MIPS and 16,000 megaflops. And we have gallium arsenide, which is the key to the serial speed. Now the module is getting pretty tiny. It weighs 8 ounces, and it's practically solid metal. And I hope you can see that there is a 4x4 array of 1-inch circuit boards. These are stacked vertically. And this is very high density packaging compared to anything else we've attempted. And the reason is it has to be to go with the gallium arsenide. If you have a factor of 3 improvement in circuit speed, you have to reduce the linear dimensions by a factor of 3. That means reducing the volume by a factor of 27. And that's not easy. If you figure the volume of the electronic part of a Cray-3, 16 processors, 512 million words of memory, the whole thing is less than a cubic foot. The rest of that is all power supply and cooling support. But the challenge here is twofold. One challenge, of course, is to package the gallium arsenide circuits in a way that will fit in the structure. Well, most people who we talked to about packaging just cringed at the requirement here because there's no room for a package. We have to package bare die. This whole package is only 1/4 of an inch thick, and it has 4 layers of boards, 4 sets of die. And in order to do that, not only do we have to package the die without, I should say, mount the die without a package, but we have to grind the die down thinner than they come from the foundry because there just isn't room for all that die material. That's the part most everybody couldn't believe. Wafers are usually processed around 25 mils thick, and we have to grind them down to 12 mils because we save half the space in the computer that way. And that seems pretty weird. But if we didn't do that, we'd have a module that was almost 1/2 an inch thick, and the whole thing would be slower by a significant factor. So we do terrible things to these little gallium arsenide die. We grind them down, then we bond great big gold posts onto them. Not little wires, but big gold posts, 3 mil diameter posts. The reason for that is the mechanical bonding of the die to the board is done with the same thing that makes the electrical connection. Namely, these gold posts go right through these little tiny boards and get crimped like a rivet, very soft gold rivets. And we bond then 16 die to each of those 1-inch boards. We have a total population of 1,024 fairly large-scale integrated circuits in this area of 4 by 4 by 1/4 of an inch. There are 4 of these modules in a Cray-3 processor, 4 by 4 by 1 inch. And that's a real advantage in the sense that the wires mostly disappear. And we have wires between them, but no big number. And so the path lengths have dropped by, indeed, a factor of 3 linearly. Typically, the average path is right around 1 inch. And that's dramatically reduced from anything that's been done before. The liquid flows right through these modules, not perpendicular, but longitudinally, Total path for the liquid is the 4 inches you see, because these modules, 200 of which make a 16-processor machine, are arranged in a circle around the top of the tank you saw. The liquid flows vertically right up through the module, flows around the die, and goes back down a supporting pipe between the octants in the machine. So total fluid travel is 4 inches, and velocity is 10 inches per second. Those numbers come out to be a very modest temperature increase over the surface, and it's quite comparable to the Cray-2 in terms of total delta T. So here we have 200 to 400 gates. 500 is the maximum that we can have in a package. Gallium arsenide circuits. 4 modules make a processor. 200 make a whole machine, including a memory. And the logic levels, if we take into account all of the paths, average out to be 6, which is about the same as it has been with 8-level logic machines. Here is the overview of system performance in the machines that I've been working on. And what I want to point out here is the vertical scale is logarithmic. Horizontal scale is linear years. Well, those of you that plot things on log paper know it's very hard to make curves go upwards on log paper. So I'm very proud of the fact that there's an upward inflection where gallium arsenide comes on the scene between the Cray-2 and the Cray-3. This is a big increase. Cray-4 is a continuation of the Cray-3. We'll talk about that a little more in a minute. But it's evolutionary, and you see we go from 16,000 M-flops to 128,000 M-flops in a period of 4 years. So we think we're at the beginning of something with this technology, and there's quite a long ways to go. And we're going to go just as fast as we can. And that's MIPS. And again, see the big inflection. There's even a larger inflection here because in the Cray-2 we could only issue instructions every other clock period. Not enough levels of logic. Here we have enough levels of logic so we can issue every clock period. And so it makes that curve even steeper. Tell you just a little more about what's happening right now, and then if you have some questions, I'll be happy to make up answers for them.